And we're going to be doing all of our work on, well, most all of the work with functions inside of the subsystem drive folder. And specifically, we're going to be looking at pieces of the drive state controller. So the math that we talked about last session was really focused on converting our 3 joystick input values into goal angles and goal speeds for each individual Swerve module. And we did all the math for that, and I'm going to show you how, I'm going to show you the actual code for that now. So that actual code is here in the Swerve math block that Alex created. It's inside a case structure because, as we'll talk about at the very end of the Swerve unit, there's some other ways to calculate the center of rotation of the robot to do some other options that aren't fully implemented yet. And so the only one that's fully implemented right now is the Swerve math block, which is what we've been driving with. So if we go in here, the inputs that we have to this block are the robot length and the robot width, so we need some physical dimensions. And then we've got our 3 joystick values. So we've got the X and the Y on, I think we decided that was the left joystick, and then the X-axis on the right stick that we're using for rotation. And then our outputs are wheel angles for all 4 wheel modules, and the power that we're going to apply to all 4 wheel modules for the drive motors. So in here we have a piece of LabVIEW that we haven't worked with before called let me make sure I get that exact name right. It's a formula node. And essentially what it does is it allows you to type code, particularly math, in text-based, like almost like a text-based language. As nice as LabVIEW is, if you're going to do a really long formula or a set of formulas, it can become really cumbersome and difficult to follow what's going on. And so this formula node allows you to type that out to make it a little bit more clear. If we go to, so the formula node can be found under the structures palette, unless I just lied to you. Oh yeah, right here, formula node. And so you can draw this, and basically on the left-hand side you have inputs, and on the right-hand side you have outputs. And so to add a new input, you would right-click on it and say add input. So say our input is X, and then if we want to add an output, we'll call it Y. So you right-click on it and say add output Y. And you do need to define the data types. So we would say, so say we're writing an equation, right? So you'd have float Y equals, I don't know, 6 times X plus 7. And so you could write your equation here, and it would go through, take whatever value is wired into X, and then evaluate this equation, and the output would be Y. You do need to end each line with a semicolon. In general, the syntax pretty closely matches MATLAB, which I don't know that any of you have worked with MATLAB yet, but kind of similar to Python in a lot of ways. So overall, it's pretty simple. I'm sure there's a lot of capabilities here that I have not used, but so far it seems pretty useful. Are there any questions about the formula node? Okay. So all we've got in the formula node is the math that we worked through on the last session. The only thing that is different from the math that there's 2 things that are different from the math that we worked through. One is that we have the answers for not just the wheel module in the upper right-hand corner, in the wheel module 0, we also have the answers for all of the other wheel modules, which again are sort of differentiated by sign differences typically. The other issue with this piece right here is when this code was originally written, there were some differences in how we define stuff. So the X and Y axes internally, I believe, are reversed in this code. And also the wheel modules start at 1 and go through 4. So they're 1, 2, 3, 4 instead of 0, 1, 2, 3. We should at some point rewrite this to follow those new conventions. We didn't want to mess with it during the build season because we had enough other things on our plate, and it's a little bit difficult to debug. And so we just change things on the output side. So like magnitude 1 goes to magnitude 0 to relabel them. And I think the solution to the X and the Y thing is, I think they got flipped at some point in here, but they didn't get relabeled fully. So we should at some point change these around to properly match our new naming convention. We do have out here, the output of the math inside the block for the target wheel angles is in radians. And so we do have a conversion to degrees. And I should also note that just like there's a formula node, there's a simpler version of a formula node called an expression node, which I believe is also in the structures palette. It is not. It is, you can search for it, expression. Oh, that's weird. There you go. Oh, that's strange. Okay, the way that I usually find the expression node block is I search for, I kid you not, I search for degrees to radians. And if you drop this block on the screen, even though it looks like a square, you get an editable expression node. You can just type in whatever you want to it. I'm not actually sure what palette the expression node is hanging out in. I'll try and find that next time I'm looking around. This works the same way as the formula node. You can really only do some simple equations in here in the sense that you don't have multiple inputs. You only have one input, and that input is called X. So you can only work, so like X is your variable, and you've got the output. So this would be equivalent to what we wrote before. what we wrote before. And it's just a little bit cleaner and easier to use. But yeah, I don't remember where it's actually hanging out at. Any questions on the expression node or in the conversion of degrees from radians? Okay. And then the other thing that we've got going on is that correction that Alex talked about for what happens if the math ends up commanding powers, motor powers that are higher than 1. And so what's been done here is all of the magnitudes that are output have been combined into an array. And the only reason to combine them into the array is that we can use this nifty block that calculates the maximum value within the array. So it's just an easy way to find the largest value out of all 4 of the wheel powers. And there's just a check to see if any of the powers are greater than 1. And if they are greater than 1, we divide all of the wheel magnitudes by that larger value to rescale the motor powers. Are there any questions about the rescaling of the powers or any other questions about the Swerve math calculations in here? Okay. So let's see. Okay. So the next thing that we need to look at is the output of the Swerve math block are the wheel powers and the target angles for the wheel modules. Does anyone remember what we have to do to the target angles or the goal angles from the wheel modules before we can input them into the PID controller for the Swerve modules?
We have to get the angular distance.
Yep, yeah, exactly. So we need to convert the goal angles into an angular distance specifically the angular distance between wherever we currently are with the wheel and where we want to be. So, you know, if we're at an angle of 60 degrees and we want to go to 90 degrees, our angular distance is positive 30 degrees because we get 90 minus 30, 90 minus 60. Now, let me go ahead and I should draw this. So bear with me while I draw a figure here. Okay. That is 0 degrees. This is going to be 90 degrees. This is going to be negative 90 degrees. And this is going to be positive 180 degrees or negative 180 degrees. This is how we chose to define the angles for the Swerve modules. This is also how the angles are defined in the autonomous modes. How they're defined in the math for autonomous modes. I think the actual path planner takes 0 to 360. I'd have to double check on that. Does anyone have questions about how we've defined the angle before I go on with talking about it? All right, so I guess I should also say that 0 angle is with the Swerve module facing straight ahead on the robot. So facing straight towards the front of the robot where the intake is. Does anyone have questions about that? Okay. So at any given time, at any given time, the wheel module is at some angle, and we are trying to get to some other angle. So so red here is the current Swerve module angle, and green is the angle that the Swerve mass VI is trying to get the wheel to get to. This is trying to command the wheel to go to. And here is my first question. How many different ways could we get from this red current angle to the goal green angle? Okay, Alex, can you describe the 2 different ways that you're thinking about?
So you can go past through the positive 90, or you can go all the way around through 0, negative 90, and then the 180s.
Okay, so this is what you're saying. This is one option. And then another option would be to do this, correct?
Yep.
Okay. Which one of those 2 options should we choose?
The shorter one.
The shorter one. So, I mean, the reason we want to choose the shorter one is we want to reduce the latency between a new command and how long it takes the wheel to actually get into position, because for the amount of time that the wheel is not in the correct position, the swerve is not swerving correctly, right? It's the wheel's moving and we're applying power, so the swerve's going to behave oddly. And so we want to reduce that and minimize that amount of time. So now here's my next follow-up question. Are there any other ways to have the same, I guess I'd say, outcome? So we've got 2 here. Are there any other ways that we could have this outcome, same outcome?
Yeah. Yes. With the other end of the swerve, since the wheel has 2 ends, we could do the same thing with the other way.
Okay, so exactly. So what Juliana is saying is that we actually have 2. So when we give a goal angle of this, of whatever this is, like 100 degrees roughly, that's saying that the wheel is pointed at 100 degrees and spinning forward. So it's spinning with, positive 1 power. An alternative option would be if we were to point in the exact opposite direction and spin the wheel backwards. So we could point 180 degrees away from this angle and then just invert the power on the motor, and we would get the same direction of motion out of the robot. Does that make sense to everyone? Or are there any questions? Okay, and so again, with this alternate angle, there are two ways to get there, right? We can again go either counterclockwise, which in this case is the longer way, or we can go clockwise and get there a little bit shorter. And so our task is twofold. First, we need to choose the correct one of these four options. So we need to choose the correct angle or its opposite angle, and then the correct direction. So we've got one of four options. And then we need to calculate the angular distance, the angle between our goal and that chosen option. And the nice thing about it is we can sort of do those two things simultaneously, because the way that we're going to choose between the angle options is by going with the angle option that has the smallest angular distance. That's the one that's going to take us the least amount of time in order to move the Swerve module. Does anyone have any questions about that concept before we go into the math? Okay, so I'm going to go ahead and skip over this latch goal block, and we'll talk about that one later. And where we're going to go is straight from the Swerve math, which outputs the goal angle, into the choose angle block. Now, the input in the choose angle block is the current wheel angle, the current goal angle that the Swerve math block is telling us to get to, and then a tuning parameter called hysteresis, which I'll talk about at the end here. We also need to know whether or not we're zeroing the wheels. I'll talk about that as well. And then the two outputs are the angular distance that goes to the PID algorithm. And then we also need a Boolean to tell the piece of code that's controlling the drive motors whether or not to invert the motor. So, if we choose this usual angle, the dark green, we're not going to invert the drive motors. They're always going to be going forward and just be pointed in the correct direction. Whereas if we've decided to go with the opposite angle, then we need to let the drive motor know that it's actually supposed to reverse its direction. Okay, so we've got two chunks of code that are duplicated, and I'm not going to go through it in exhaustive detail, but essentially what we have going on is the following. We've got our goal angle, which normally is what's coming from the Swerve math. We do also have the ability to switch the goal angle to be 0 degrees if we press the 0 wheels button on the driver station. So on the driver station, there's a 0 wheels button that we found useful, and that forces the wheels to go to the forward position so they're ready to be calibrated, which we'll talk about later. If we just look at this top section, what is happening is we're calculating two angular distances. So first we're calculating the easy one, which is the goal angle minus the current angle. So that would be, if we're looking at this red line and the darker green line, we'd be calculating this 100 degrees minus whatever that is, 30 degrees. And so we'd get a 70-degree angular distance here. And it is important that it is the 100 degrees minus the 30 degrees here, in the sense that we do care about the sign of the subtraction. We don't just care about the absolute value. Because what the PID algorithm needs to know is not just how far away it is, but whether it should be spinning the wheel counterclockwise or clockwise. And we've defined counterclockwise as positive in the rest of our code. So if we're at 30 degrees and we need to get to 100 degrees, we're going to spin counterclockwise 70 degrees in order to get there. Does anyone have any questions about that? Okay. Now this next block right here is a little bit annoying to talk about or to describe, but really all that you need to know, and you could recreate this is calculating the other angle, and it's got all these statements about whether or not the angle is on the 0 to 180 side or the 0 to negative 180 side, because it's got to do the subtraction across what we call discontinuity. So from here, from 90, 90 we go 90, 80, 70, 60, blah 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 blah, 10 degrees, 5 degrees, 0 degrees, negative 5 degrees, 10 degrees, or negative 10 degrees, negative 15 degrees. So this is a smooth transition as we go around the 0. But as we go around the other direction, we're at 170 degrees, 180 degrees, and then all of a sudden we jump to negative 180 degrees, negative 170 degrees. So there's a big jump there, and we've got to handle that with a subtraction. And so all these 180s minus the other things are to basically calculate, the distance from the current angle to this 180, and then the 180 to, let's see, or sorry, it'd be like this, it'd be like calculating this angle from the red to the 0, so it'd be like 30 degrees, and then you're gonna have to add that to the angle from, I think typically what you basically do is you're calculating, this angle between the red and the 0, and then you've got the 180 degrees from the 0 to this 180 degree marker, and then you're also calculating the angle from the 180, or sorry, from the goal angle to the 180. So you're going to sum this angle. Let me see if I can draw that. You're going to sum this angle, and this one, and then this one. And you can write all of that out, and then when you simplify it all, you can express it this way. So the reason this is kind of ugly is that it's been simplified, so it's easier to write in LabVIEW, but it's a little bit harder to follow. But it is essentially the summation of all these three pieces. Alex asked if we could just take the supplementary angle and then go the opposite direction. I couldn't tell you. I haven't used the term supplementary angle in a long time, so I can't quite remember the definition. If you did do anything like that that works, you're going to get the exact same answer, 180 minus x. 180 minus x.
It's like 30 and 150 are supplementary angles, and 30 and 60 are complementary angles. Like they add up to 180.
Yeah, I could see, basically being the opposite, right? So maybe a simpler way even would be, if you know this angle, that's maybe even a simpler way would be if this angle is, what we say, 70 degrees, then the other angle should actually be 360 minus that, right? It'd be 360 minus 70, so it's going to be 290, which I think is what you would get if you did the supplementary approach. The only thing that you have to be careful about when you do like that is you're still going to have to handle the signs so that you maintain the correct signage as you do the subtractions, because you could also have the case where this value here on the shorter angle is a negative instead of a positive. These could both be, or just one of them could be on the opposite sign, like on the opposite side. And so I think regardless of what you do, which I think, this looks like it's basically the same thing here. We got 180s minus stuff. You still sort of end up needing just a little bit extra in order to handle all of those signs. Does that make sense, Alex? Okay. Yeah, I mean, I expect that any of these trig approaches, they're all going to be equivalent. However you want to do it. Sort of the annoying part is handling the signs to make sure the signs work out. So what you've got going on here is, and maybe this should be labeled at some point, at the output of this minus, we've got one distance, and the output of this one sign distance. And at the output of this minus, you've got the other sign difference. We're going to take the absolute values of both of those sign differences, and based off of which one is smaller, we choose the smaller signs difference, the smaller magnitude distance, and then we reapply the signs, so we make sure we preserve the signs. And so the output of this select block then is the smallest angular distance option, either it's counterclockwise or clockwise for the darker green line, and that's the output here. Does anyone have any questions about this block of code here? Okay. This block of code is completely duplicated over here. The only difference is that instead of it being the goal angle that's going into the math, we have the opposite of the goal angle going into the math. So here we're calculating basically the 180 minus this angle, so we flip it around. The extra stuff here is to handle again the sign oddities, just to make sure that we don't have any weirdness with how the signs are interpreted. And so we do the exact same calculation, but instead of it being the goal angle, it's the 100. It's the opposite of the goal angle, and we get the optimal or the smallest angular distance for going to the goal angle, to the opposite of the goal angle. Does anyone have any questions about the lower half where we're working with the opposite of the goal angle? Okay. So now we're down to two options. We still need to get this down to one, to the best option. So now we need to compare whether or not it would be better to go with the goal angle or with the opposite of the goal angle. Go ahead and let me do the following here. I'm going to cut out a piece of code so we can ignore it for a second. So does everyone see how I cut this out? So we've got this set here connected directly to the and. Okay, so with the code written this way, all that we've got going on is doing the absolute values again, and again checking to see which value is, which angular distance is smaller, and picking the smallest of those angular distances. So it's identical to these operations here. The only added thing is that we also need to, based off of whether or not we pick the goal angle or the opposite of the goal angle, we also need to trigger the whether or not to invert the drive speed so that the wheel will go the opposite direction. Does anyone have any questions on that portion or on inverting the drive speed? Okay, so let me recover this last piece of code, and let me ask the following question. What problems do you think might arise if we give the robot the ability to choose either the goal angle or the opposite of the goal angle?
When we're on the edge of being between, when there's not a big difference between which one is optimal, if like the driver flickers their, if the driver flickers the joystick a little bit, that can cause a big change in whether or not we should invert it.
Yeah, exactly. So if the wheel is currently rotating towards its goal angle, and while it's rotating towards the goal angle changes a little bit, and we're right on the edge between whether or not it's better to choose, the goal angle versus the opposite of the goal angle. Then as the wheel moves, and if that goal changes a little bit, the decision about which one it should take could change. So, for the first 100 milliseconds of the wheel is moving, it's saying, okay, I should be going to the goal angle. And then something changes a little bit, and now it's like, hey, it's actually better if I go to the opposite of the goal angle. And so you could end up in a situation where the wheel will bounce around between trying to get to the goal angle versus the opposite of that goal angle, and it's trying to get to that shortest route, and it'll just sit there oscillating back and forth and never actually get anywhere. And so we want to avoid that problem. Does that problem make sense to everyone as it's described? So does anyone have any thoughts on how we could mitigate this problem, how we could keep the wheel from having this behavior?
You could make sure that how far off it is above a certain threshold. Yeah,
I mean, exactly. So basically you say, okay, once you've made your decision, like once you've decided to go this way, don't change your decision again unless the benefit to changing that decision is a lot. So instead of that benefit having to be, 0.1 degree, that benefit has to be, 20 degrees. So it has to be a lot better to go the other way than to just keep going the direction you were going. This approach is called adding a hysteresis to your system. Hysteresis is just a fancy term for something behaving differently in one direction versus in the other direction. So we've used hysteresis on the auto shifting from last year. So there's a very similar problem. If you wanted to auto shift at 5 feet per second, then as the robot passes near 5 feet per second, we would have a risk of it oscillating between being in high gear and low gear as it's right around 5 feet per second. So what we did was we said, okay, if you are currently below 5 feet per second, then I want you to switch into high gear once you get to 5 feet per second. But if you're above 5 feet per second, if you're already going fast, then I don't want you to switch into low gear until you get down to 2 feet per second. And so you end up with this zone where the decision that it makes is different based on what side of the zone it's on. And so it avoids this sort of oscillation behavior. The other place that this was used this year was on the cowl angle. So the cowl would change angle based off of its distance away from the target. Again, we don't want to have an oscillation right at the border of the decision. So if it was already close, it stayed, I think, retracted for a little bit longer than if it was coming from further away. And this atom is one of the frustrating things that we ran into is that for you, the angle that we wanted to be at with the current shooter, that decision point for all the way forward versus all the way back was very close to where you wanted to be, where you need to be shooting from, right around the initiation line. And so that meant that the behavior of the system could actually be a little bit different depending on whether or not you picked up a ball off of the Alliance Station wall and then backed up to the initiation line versus if you grabbed the ball in the trench and drove forward to the initiation line. Those two actions would actually, even though you ended up at the same point, would actually result in different cowl angles using the targeting computer. And so that was one of the things that made the targeting computer kind of challenging. Does that make sense? Does anyone have any questions about that? Does Adam have any complaints about the Cal angle choices? Okay, so the way the hysteresis is implemented here is we're checking to see if not just whether or not just to see which of these angular distances is larger, but checking to see whether or not the difference between those two angular distances is larger than our hysteresis, which we chose, I think, as 10 degrees, worked pretty well. And if it is less than 10 degrees better, then we stay latched with the choice that we made before. So we continue to choose either the, if we chosen the goal angle before, we stay choosing that one. And if we were previously choosing the opposite of that, then we're going to stay choosing that. We only put in the new choice if choosing that new choice would be better, would save us more than 10 degrees of travel distance. Does that make sense? Are there any questions about how the hysteresis is implemented in this code? Okay. Any questions or comments about choosing the angle, this sub VI here? Okay. Let me close that. Okay, so at this point we have an angle that we can send to the PID controller on the Swerve modules. Just to refresh everyone's memory, I'll go ahead and load that up. So those are located in periodic tasks. And so they are located right here. So the output of this chose angle block goes into the global variable wheel 0 azimuth distance, and that comes out here in the actuator loop going into the PID controller, which will then set the power for the Swerve modules. Okay. Does anyone have any questions about, or any questions or comments about that transfer with the global variable or with the PID loop? Oh, and I guess I should also, the other comment I should make here is that just recall that we're using the PID loop a little bit opposite from how we normally do it, because what we're sending to it is already the angular distance. The goal for the PID loop is always 0, so we're always trying to get to a 0 degree angular distance. And then all we're doing is changing the process variable, which is how large that angular distance is, and we're always trying to drive it down to 0. So our goal for the PID controller stays at a constant 0. Okay. So the next thing that we need to talk about is everything here, we've been working with angles, but the physical sensor that is on the Swerve module, so the azimuth encoder, does not give values in angles. Instead, it gives values in, well, if you don't do anything special to it, it gives values between 0 and 5 volts. If you do what I'm about to show you, it's going to give a value between 0 and 1. And so we can see where we initialize the azimuth sensor inside of the begin VI. So that is under our, let's see, that is under our initialization folder. And then if we go to begin, and then we go to initialize sensors, what we've got is the analog input that the azimuth encoder is going into And we have a couple options. We could open it as just a raw analog input, which would be from 0 to 5 volts as the output. There are some advantages to instead opening it up as a potentiometer. One advantage, which is sort of minimal, is that it rescales it from 0 to 1, which may or may not be easier for you to work with. The other nice thing is that technically this also does a check for you. So the wheel encoder actually doesn't have to give between 0 and 5 volts. Depending on how it was manufactured, it may only give between 0 and 4.8 volts or some other random value. And if we treat it as a potentiometer, first has already written the code to basically check that value and rescale it from 0 to 1, so we don't have to deal with finding out that we don't have to deal with explicitly finding out that 4.8 maximum value. So the output of any potentiometer read blocks will be from 0 to 1, with 0 being one position on the azimuth encoder and 1 being a full 360 degrees back to that original position of 0. Does anyone have any questions about the azimuth encoder, physically or in code? Okay, so we do need to convert the 0 to 1 to convert the 0 to 1 to 0 to 360 degrees. Does anyone want to suggest some options for doing that conversion between 0 and 1 to, actually, I guess, sorry, negative 180 degrees to positive 180 degrees? So, Ethan, what are your thoughts on how we might do that conversion?
Could you repeat the question real quick?
Yeah, sure. So we've got a sensor value that is going from 0 to 1, and what we really need are degrees out of that. So we need something that's going to go from negative 180 to positive 180.
Okay, so I mean, when you just set a change in voltage, so between 0 and 1 to like a certain number of degrees, so like you define like from 0 to 0.0 something is 1 degree, and you just look at that change.
Yeah, so you could do that. So mathematically what that would look like is the following. If I can draw here. So we could create a function where on the x-axis we've got, we'll call this analog input value. Oh wow, apparently we're doing red. And on the y-axis we have degrees. And our values are going to range from 0, oops, O, 0 to 1. And we want our angles to range from negative 180 to positive 180. Okay. So what we want to do is find a function that is going to map these value, the 0 to 1 values to negative 180 to positive 180. Now, does anyone want to comment on what kind of function we could use, or any problems that we might have with mapping a function, creating a function that would allow us to convert 0 to 1 to negative 180 to 180?
Do we want to use something triggy?
It doesn't need to be anything tricky. I like that word, tricky. we could use, so fortunately the sensor is linear, so a 1 degree change is, so a 5 degree change is 5 times as much as a 1 degree change. So you can use straight lines to do this. Can you think about what might be some problems with actually using a straight line to do this though? Or a single straight line, I should say. So Amelie asks, can you use a piecewise function, which is a bit of cheating since she's the one who wrote it. I don't know if she remembers, but she's the one who did that. I don't know why she's asking it as a question. But yes, so if I were to draw a single line here, if I were to go from say I wanted 0 to be positive 180, the problem that I would sort of have is as I drew this, right, and then 1 is negative 180. Okay, so I guess I should say in this particular case, the way this is set up, this technically works in the sense that as you go from 0, you start out at 180, and as you get all the way to 1, you go to negative 180. And then the sensor wraps around and you're back at 0. And so you're back at positive 180. So this would work if you set 0 to be 180 degrees. Does anyone have any concerns about setting 0 to be positive 180 degrees?
Does it fluctuate a lot?
Hopefully it doesn't fluctuate a lot. That's one of the reasons that we're using a sensor.
Oh, does it never ever like actually become true 0? There's always like 0.001 and then it won't like reach your thing.
It does get pretty close to true 0. Even if it didn't get close to true 0, I think it would still be okay in this case. So here's a question for Adam. Adam, what angle did you install the azimuth encoders in? So Adam may be thinking really hard right now.
I understand. I understand.
Okay, go ahead, Alex. What is it?
So, because he doesn't know what angle he installed them in, 0 doesn't actually equal 0.
Exactly. So my best guess is that Adam did not remember or notice exactly what angle he happened to assemble the Swerve module together. Furthermore, as we discovered at Little Rock, that angle does the gears and everything tend to slip, and so over time, the assembly can change. And so, in our math, we really need 0 degrees to reference straightforward on the robot, but exactly which voltage value of between 0 and 1 it is corresponds to straightforward is not always going to be 0. In fact, it's pretty much never going to be 0. And so we need to have a way to have an arbitrary an arbitrary value on the sensor correspond to straightforward. And that's the calibration process. And that's why we need piecewise functions. So let's consider the following example here. So I've got an example. What did I decide? Okay. So I wish I could share my notebook, but I have not been able to get that to work properly. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And then Okay, pretend that these are all evenly spaced and they're beautiful. And so we've divided up our, see, each tick mark is at 0.33, wait, 1, 2, 3, 4, 5, 6, yeah. There we go, 1 right there. Okay. So we divided up, so the tick marks are increments of 0.33333. That's just what I drew in my notebook before I realized that was inconvenient. And let's say that at this particular time, the straightforward on the robot corresponds to, let's see, 0, I said that point right there. So, sorry, there are increments of 0.166667. So this is 0.833, right? And I'm sorry, I should have chosen different numbers, but I did not. Does that make sense, or did I kind of butcher those numbers there? So the star being the location of the sensor that corresponds to 0 degrees, that is straightforward on the robot. Okay, so with that position known, then we sort of know what needs to happen here. Let's see, the 3 to that. So we've got a line of a known slope, which is that, you know, we've got this conversion between degrees and the 0 to 1 units. So let's see, how do I describe this? So just like before, let me do this. So this was that line that we had before, right? No matter where the 0 point is, the slope of this line has to stay the same, because this is the conversion, you know, the multiplication that you're going to do between degrees and the 0 to 1. So we've got to use the slope of the line, no matter what we do. The problem is this has got to get moved to here. And then we have this issue of, oh, wait, what about the zone over here and the zone over here where we're going off the axes? And so what we need to do is create piecewise functions that have the same slope, but let's see, extend differently. So let me do this. So we've got, what it ends up with is this. So let me, and I'm going to try and match the slopes here as best as I can. Okay. So that becomes our piecewise function where, you know, when we're over here, we're going from negative, positive 180 all the way down to whatever, I think negative 60 degrees is about here. And then as we roll around, we've got to still stay, or that this, if this is negative 60, then this better also be negative 60. So that when we wrap back around, we start again at negative 60 and then keep going down negative 180. And then we do the jump back up to 180. So all this is a shift off of the 0 from what we had before. But we do now have to represent it as a piecewise function in order to handle the fact that this 0 position could be anywhere along the x-axis. Does that make sense, or did I butcher that? And does anyone have any questions? Okay, so and then the value that we care about when we do a calibration is this value right here. So that looks like it's right around 0.33. So this becomes the value that we use, the sensor value that we use in order to do the actual Swerve module calibration. And every time we change the calibration, what we're changing is we're moving, can I not select multiple things? Oh. Okay, apparently I can't select multiple things, but we're moving this value back and forth along the x-axis, and we're shifting the piecewise functions. And if we were to, get really perfect and have 0 line up with 0, we'd shift this all the way back, and this would be the original problem that we had before, where we're perfectly aligned up. Let's see. And then let me just sort of show an example of this real quick. So let's see here. No, well, that's not super useful. I'm not going to show that example because I don't know that it's super useful to show here. But does this make sense, or are there any questions about how we're going to convert the 0 to 1 value into a positive 180 to negative 180 degree value? Okay. So in that case, I will go ahead and show you all the code for that, which I'll normally put together. Actually, I can't remember. I feel like Amelia also worked on it, and then Amelie worked on it. I don't remember. I think there were a couple people who worked on it. So that code is not in the drive state controller. It is under the sensors folder, and we're going to look at get high priority sensors. I think. Okay. So right here is where we are reading the values from the azimuth encoders. And then the first thing we need to do is do the conversion from the 0 to 1 value into those negative 180 to positive 180 degrees, which is down inside this block. And all this math is doing is implementing the 2 piecewise functions. So there's a check to see which side of the calibration point you're on, right? If you're on one side, if you're on the left side, you're using, the first piecewise function. And if you're on the right side, you're using the second piecewise function. And the rest of it is just the equation for the line and setting the slope and the y-intercepts, essentially. And so all this is an implementation of the piecewise linear functions that we just drew. Any questions on the actual code version of this? Okay. So the next part that we got to do is we do need to be able to calibrate the wheels, because that position is that 0 position is going to change, and it's obviously going to be different for each one of the 4-wheel modules. The way the calibration is handled is when the calibrate wheels button is pressed on the driver station, we read the current wheel position value and insert it into a feedback node and store in memory that calibration point. Now that works great as long as the robot is turned on. As soon as we turn off the robot, we are going to lose the value that we have stored in the feedback node. So that's the difference between RAM and the hard disk on the hard drive that we talked about before. And so in addition to storing it in memory, when we press calibrate, we also take all of the values and put them into an array, and then save that array of calibration points as a file on the RoboRio. So in the calibrations folder on the RoboRio, there's a file called Swerve calibration that contains these points. And then when the robot boots up again. We read the values from that calibration file. We check for any errors, and then if there are no errors, we go ahead and use the values that are stored inside of the calibration file in order to calibrate the wheel module. So we remember the calibration from the last time. Again, the reason that the whole file read is inside of the case structure is because the file read operation is expensive, and we only want to do it when we first boot up the robot, and we don't want to keep reading files the entire time the robot is on. Does anyone have any questions or comments on the calibration process for the Swerve modules? Okay. So at this point, we're here, and we could actually have a fully working, we're here, sorry. We could have a fully working Swerve drive in the sense that I think we were at about this point, minus the ability to save the calibration file, when we were driving right before New Year's Eve of 2019. So that's what's required to get the robot driving on the ground. Everything that we're talking about after this are improvements to the Swerve code in order to allow the driver to have increased control and increased responsiveness from the system. So the next item that we have on our list is field-oriented versus robot-oriented control. Does anyone remember the difference between field-oriented and robot-oriented? So I haven't picked on Mr. Shanafield at all today. Does Mr. Shanafield know the difference between field-oriented and robot-oriented control?
Field-oriented, you can drive straight and turn, I think, right? And then it'll always go back to straight, and robot-oriented, it won't.
Not quite. So that's another piece of the code. So the auto straightening is a different piece of the code. We've got Adam on here. Adam, you want to enlighten us with the difference between field-oriented versus robot-oriented control, and maybe also talk about what works and what doesn't work?
It doesn't count if he doesn't speak. If he types it in, it doesn't count.
I'm not sure that he has audio. I think he has to type.
No, that's not him then. I don't believe it.
Well, while we're waiting for Adam to maybe type, Ethan can also help answer.
Okay, so field-oriented controls, basically when you're making movements on the robot, the straightforward and, driver-oriented. That's what I'm about to say. When you turn or make any movements, forward relative to you is the same. So if I push forward on the stick, it's going to go away from me. If I push back on the stick, it's going to go towards me from the driver. And then field-oriented would be if I turn 90 degrees and then go forward, I'm going to go forward in the direction I just turned 90 degrees to. If that makes sense.
So the definitions are correct, although they are reversed. So field-oriented is the first one that you described, where if you press forward on the joystick, you're always going to go away from the driver. And if you press backwards on the joystick, you're always going to come back towards the driver, regardless of the orientation of the robot. And then robot-oriented would be you're always going to go forward relative to the forward direction on the robot. So as Ethan said, if you rotate the robot 90 degrees and you press forward on the robot would go, I guess, to your left, which would be the forward direction relative to the robot. And I think, you know, most of you have driven the Swerve drive at least a little bit. Some of you may not have driven it at all. Swerve drives tend to be very, very difficult to control in robot-oriented mode because you have so many different things to worry about. And particularly this year, our robot was very square and kind of symmetric, which makes it hard to see which way is forward. And so you end up having a lot better control. It's a lot easier for the driver to control the robot with it in field-oriented control. So does anyone have any questions about field-oriented versus robot-oriented control, like what they physically mean? Okay. Does someone want to talk about how we might implement, like what sensors or what information do we need in order to do field-oriented control? Alex?
We need IMU and 4 wheel encoders.
Okay. We probably don't need we need the wheel encoders for other things. I don't know that we need them specifically for field-oriented control. But yes, we do need an IMU to do field-oriented control. And the nice thing about field-oriented control is that even though it sounds complicated, let me show you the code for field-oriented control. So in our drive state controller, we've got two options. We've got robot-oriented, which does nothing to the data lines. Oh, I should say, so the data lines that are coming in are the X and Y joystick values for the translation joystick. So we're not going to touch the rotation joystick at all with this because counterclockwise and clockwise don't change based off the robot orientation. All we need to do is look at the X and Y commands from the translation joystick. So in robot-oriented, we do nothing. It goes through the Swerve math just as normal. And then in field-oriented control, we do all of this math right here, which is pretty much just like two operations. This VI takes as an input the X and Y values from the joysticks and the current angle of the robot. I took this out of, well, I looked to see how Mars did it and took this and then found out that this is actually taken from the WPI library's mechanism drive code, which I found out was then taken from the Cheesy Poof's C++ function. So this exact piece of code's traveled a little bit. And all we're doing at the very beginning is converting from degrees into radians. And then we're calculating the sine and the cosine of the robot's current angle. And essentially, all we're doing is multiplying the X and the Y positions by either the sine or the cosine, and then doing some subtractions and pluses and additions. And we can work it all out if we wanted to, but essentially all it's doing is, if you normally have, if you normally have, your X and your Y axis like this, and if your robot rotates, robot rotates so that it's at this angle. Oops. That's why. Literally, all this math does is rotate your X and your Y so that they're lined up with the direction that the robot's pointed. And this becomes your X. That little symbol in math is often used to say prime, so it's X prime, and then Y prime. So you could do it a couple of different ways, but essentially you are just rotating your coordinates so that they're always pointing the same direction as the robot's pointed. So whenever the robot is changes its orientation, your joystick values automatically get altered so that your so that forward on the joystick is let me see. Hang on one second. I want to make sure I don't have this backwards. X and Y. That is pointed that way. And okay, sorry, I should do this slightly differently. It would be better to think of this as rotating the axes to be the opposite of how the robot's rotated. So if you've rotated the robot, say 30 degrees this way, the coordinate systems get rotated the opposite way, the same amount, so 30 degrees the other way. So you can sort of think of it as if you were the human trying to do this, you would see that the robot had rotated 30 degrees, and you would change, let's do it this way. Let me show you an example where you could do it with the human. So say instead, let's do this. Let's say that the robot rotated a full 90 degrees. So it's now pointed facing your left. So this was forward ahead of you. Now it's facing your left. So if you're the human and you want to go downfield, you know that you now need to be pressing on the right. Instead, you know, if you were pressing forward back on the joystick here when it was like this, and it was oriented along the x-axis front of you, when you turn 90 degrees, you now know that you've got to push left right instead of front back because you're rotating 90 degrees. So the math is going to do that for you and rotate this so that when you press forward on the stick, you're actually, you know, the commands are actually going to the swerve math then are actually, have been rotated. So you're now pressing, it's like doing the math for you to now know that you need to press left, right instead of front, back in order to go down the length of the field. Does that make sense? How it handles that rotation conceptually? Are there any questions with that one? So yeah, really all this block is doing is handling this thing that you could theoretically do in your head where you change the joystick values that you're applying based off of the robot's angle. And it's doing that a lot faster and a lot more accurately than a human could do that. Okay, so let's see. Close that. Okay, so the next part that we have here is talking about things that we normally have to do with driver controls and drivetrains. So it's pretty typical that you need to have some sort of deadband in the joystick values in order to make sure that the robot doesn't twitch. Can anyone talk about the deadband and why we have it?
The joystick value may not be completely accurate. So even if you're not actually moving the joystick, it may say that the joystick is some very small value. But then that means that the robot will start to move in some random direction when it's not supposed to and no one's touching the joystick. So we have small deadbands where if the value is tiny enough, it doesn't move.
Yeah, so exactly correct, Joanna. So, you know, the joystick values range from -1 to 1. Theoretically, if you're not touching the joystick, all the values should be 0. Usually we see them at about 0.02 or 3. Turns out that when you drop the joysticks repeatedly, that default value starts to get higher to like 0.05, 0.07. So that's another reason to not drop the joysticks repeatedly. And we don't want the robot to move while we're doing that. And so we incorporate a deadband where if the value is below, the joystick value is below a certain number, then we don't move at all. Now, there are 2 ways to do a deadband, a good way and a bad way. So if we've got another function, another plot here where I'm just going to do half of it and I can do the negative half. Where on the x-axis we have the joystick value, like I'll say the raw joystick value. And the y-axis we have the good joystick value. So this is the value that's actually going to, say, the swerve math in this case. And let's see. We're going to go from 0 to 1, 0 to 1 on both of these axes. And one way to do it, so normally without anything special, that's what the function would look like, right? Y equals x. So the good joystick value would always exactly equal the raw joystick value. Sort of the simple way to do a deadband is to simply say that any value less than the deadband value of, say, 0.05 should just be 0. So we would do this. Yeah. And that would at least prevent us from moving when the joystick isn't pressed. Does anyone see any problems with this approach? Lindsay, what do you think?
Can you repeat the question?
Sure. So one option for creating a deadband is to simply say that, you know, for any raw joystick value below 0.05, we should just output a 0 power to the motors. And then after 0.05, we just use the values as normal. And so that function would sort of look like this, where we've got 0 all the way to 0.05. And then after that, we've got our straight line. Do you see any potential challenges with controlling a robot this way?
Would it, if they moved it out and then moved it back, would that be a problem?
So work through that a little bit. So what do you mean?
Would that account for them accidentally moving the joystick?
I think moving a little bit forward, a little bit back would probably be okay. So let me make this a little bit more stark here. What if the joystick's been dropped a lot because we enjoy dropping joysticks. And the deadband was very large. So maybe the deadband is, instead of 0.5, it's 0.5. And so now our function looks like this.
Lab, computer scientist, Dr. Tara Q.
What do
Mom,
you think about that, Lindsay?
sorry, front. Continue.
So if we've got a much larger deadband, and so our function looks something like this, what do you think would happen?
It wouldn't allow for them to get small increments or just a little bit of movement.
Yeah, so it'd be very hard or impossible for them to go at low speeds. They would literally go from 0.00000 to 50% power. So there would be this very steep jump as you come out of the deadband. And so a better approach, or a more robust approach, would be, in addition to having this portion here where you're at 0, you also change the slope of this line so that its tail end meets at the bottom. So you go straight from, instead of making this jump, you go 0, 0, 0, 0, 0, and then you start gradually climbing up. This is essentially remaps the joystick so that you're ignoring the first part of the joystick, but you can still use the second half of the joystick range in order to take the full range of power levels, so you don't get that jump. Does that make sense? Does anyone have any questions about deadbands? Okay. So the other thing that tends to come up, not just in Swerve drives, but in pretty much all drivetrains, is that generally the driver needs substantially more control at lower velocities than they do at higher velocities. Or the way I should really say that is, the driver would love if the programmers could give them, very fine control at all speeds, and it would be their best friend. Instead, unfortunately, the programmers have to go over to the driver and tell them that that's not possible. Instead, what they can say is, well, I can't give you really high control everywhere, but I can give you really good control in some regions, and at the expense, at the cost of reducing your control in other regions. And typically what we do is we give the driver more control at lower speeds and better control at higher speeds. So what that would sort of look like is, if instead of a line, we could start out with just we have a function that looks like this. So we'd start out like this, and then all of a sudden we would jump up to, I guess, like that, right? Let me see if I can, or I guess technically, maybe as accurate as I can be here. Right. So we'd have a function like this, where for very low speeds, so if we go from 0.5 to 0.7, maybe we only go up. Let me be a little more explicit. Say we go from 0.5 to 0.75, so we go half this distance again. But instead of going up 0.25, we only go up 0.05. So that would be like if I wrote in, I apologize, sorry, I heard to sort of line things up here. If that right there was 0.75 on the raw joystick axis, its corresponding value would maybe only be 0.05 here. And so that would look like, oops. right? And so what this means is that you're basically using a fairly large portion of the joystick in order to make fairly small power differences in the motors. The more region of the joystick the driver is able to use for this, the more exact they can be, because small little twitches in their hand and so forth make less of a difference. Make less of a difference in the power output. The downside is the more of the joystick that you use to make these really small changes means that you have less of the joystick to sort of cram in the rest of the power range, because you still want to be able to go at full speed. And so you end up then having to cram the rest of it. So going from 0.75 to 1 here now takes you from 0.05 all the way to 1. So 95% of your power change occurs here and just 25% of how much you're moving the joystick. And so this is the trade-off between more control at low speeds, which is great, to at the expense of less control at high speeds, which is not ideal, but may be workable depending on the game. Does that make sense to everyone conceptually? There are a couple of different approaches to doing this. Some people, including Mars for a while, experimented with doing, Ethan says yes, but it's kind of depressing. So I'll circle back to the depressing part because there are some solutions. So people have played around with doing piecewise functions, piecewise linear functions. They've done spline interpolations to make it really specific. In my opinion, the driver really can't notice which technique you use. What they really care about is it being a very smooth transition. And so typically we do the following, where we say the good joystick is equal to the raw joystick to some power. And if you set the power to be, if power equals 1, that's a straight line. So that's this one here is power equals 1. And then as you increase the power, so if you go up to, you say power is, I really shouldn't call it power. I should call that, I'm just going to call that exponent here, so we don't confuse it with motor power. So as you increase the exponent to, say, 3, that's a much, I guess I'd say, much shallower than much steeper curve. So, oops. If you've got some different line options here, a power of, x squared, so power of exponent of 2 might look like this. And then if you did like x to the 5th, you'd look like this. You'd look like this. So again, increasing the power flattens out the initial part and gives you more control at the beginning, and then but compresses the remaining rate, compresses the rest of the power range into the smaller joystick range and gives you less control at higher speeds. Does the usage of the exponents to do this curve make sense? I don't know how much you all played with functions to the power of different exponents. Okay. So one of the things that Ethan says is that this is kind of depressing. I agree. There are a couple of solutions that different teams have tried. So a lot of the higher end teams use, instead of using game pads, they use fixed joysticks. that are mounted physically to the control board, the operator console. The reason they do that is those physically have more range, and so you can have more control over the robot's actions without having to go to such steep curves, because you can make smaller adjustments on the joysticks. So that's one approach, sort of from the hardware side. Another approach that happens, another improvement to this algorithm, is something that the cheesy proofs have done in the past. They don't do it every year, but instead of mapping the curves to mapping this to the raw joystick value, they actually map it to the robot's actual ground speed. What this allows is that even if the robot is going slowly, so it'd be for situations where the robot's going slowly, but you've told it to accelerate, you maintain your fine control until the robot actually gets up to speed, versus losing that fine control as soon as you tell it to accelerate. So that's another tweak that we could consider making. I don't know if people do it with Swerve drives or not, but that's pretty common for, or I don't know if it's pretty common. I've seen the cheesy proofs and no one else do it for 6-wheel drive robots. Does anyone have any questions about either the deadband or the scaling of the joystick values? Okay, so for the rotation control on the Swerve drive, this is pretty simple. Let me see. We can directly apply these functions where this first portion of the code is calculating the adjusting for the deadband, and then this block right here is doing the power of, so x to the power of exponent y. And those, both the deadband value and the exponent, are tunable parameters for each driver. And this portion is pretty easy. This is also what it would look like on a 6-wheel drive or just a normal butterfly drive robot. Now, if we want to do the scaling to the X and Y axes on the translation joystick for the Swerve drive, can anyone think about what kinds of problems we might run into if we do this exact approach for the translation component of the Swerve drive? What do you think, Amelie? What might be some limitations of applying this to the X and Y axes on the Swerve drive? Maybe, oh, there we go.
I don't know.
I don't know, okay. Alex, any thoughts?
Is it because if you just do the translation stick, you won't get the rotation stick, and then when you put them together, it doesn't work as well?
You're getting close. So the rotation stick versus the translation stick will work out okay. But you are correct that when you're working with the translation stick, you got to be careful about something so that things still work out. What values is the Swerve math extracting from the translation stick? Like, what is it converting this into?
The magnitudes and stuff.
The magnitudes, and what's the other thing? What's the and stuff?
Speed and add the, oh shoot, the angle.
The angle. So if we were to apply the scaling to the x-axis of the joystick, and then apply the scaling the y-axis of the joystick, because we'd be using this nonlinear curve, if say let me put it this way, if the x-axis, the raw x-axis was 0.1 and the raw y-axis was 0.2, that would result in some magnitude, great. It also results in a very specific angle, right? Because we're taking the inverse tangent of that 0.2 from the y-axis over the 0.1 from the x-axis, right? If we were to then apply the deadband and the curve, the power curve to those x and the y's independently, we would rescale the 0.1 by a different amount than we would rescale the 0.25 because they're on different parts of the curve. And so the inverse tangent of the scaled y over the scaled x would no longer be the same. And so the angle that we're commanding the robot to go to also changes. And so even though the driver is still holding the joystick in, at the angle that they want to hold want the robot to go in, it's going to be shifted, either clockwise or counterclockwise because the scaling is different. And so, in fact, as you were to, if you could perfectly hold the joystick so that it was always at the x and the y positions were always at the correct angle, at the same angle, and you just increase the power like diagonally away from the center of the joystick, the angle that the robot would translate in would actually change as the different axes get scaled differently. You'd get different angle goals. Does that make sense, Alex?
Yep.
Okay. So we've got to be a little bit more careful with applying the deadbands on the translation stick. Basically, what we did here was instead of applying the scaling in the deadbands to the x and y axes independently, we only applied them to the magnitude portion of this. And so we go ahead and do the the Pythagorean theorem magnitude. So this x squared plus y squared square root. And we calculate the magnitude, and that magnitude is our raw joystick value. So that's the x-axis here. And then we apply the deadband and the power function. And what we get out here is a scaled magnitude. So if our magnitude was below the deadband, our scaled magnitude is now 0. If our magnitude was, say, 0.5 before, and we had a squared, here, like if our exponent was a power of 2, then this scaled, the scaled magnitude would now only be 0.25, right? It'd be 0.5 squared. And so we would have scaled the magnitude, and all we do is come back and multiply the raw x and the raw y values both by that scaled magnitude value. So if the joystick values were, or sorry, I should clarify. The output at this point is that scaled power. So coming out of the power block here. The divide that's going on here is dividing that scaled power by the original magnitude, so that what we have is the fraction of the original magnitude that the scaled power is. So let me write that out. That's sort of hard to say. So if our original x squared plus y squared square root equaled 0.5, so the total magnitude of those is 0.5. And if we had an exponent of 2, and for right now I'm just going to assume that we don't have a deadband because it's going to make it a little bit easier to do this, then at this line here, at this line right here, this output here, that would be 0.5 to the power of 2, which equals 0.25, okay? And then we're going to do this division where we go 0.25 divided by the original magnitude, this line right here, which is 0.5, which equals, conveniently, 0.5 or 50%. And then we would multiply the X and the Y joystick values both by 50%. And so we would scale them both the same. And so then when we go to do the arc tangent, so at some point we've got to do this arc tangent to get the goal angle. So we've got angle equals arctan of y prime over x prime. They're the primes because they're coming out of that out of the field-oriented control block. Then we would have, and that's what it is normally. Then we would have arctan of 0.5 times y prime divided by 0.5 times x prime. And no matter what this fraction, no matter what this percentage ends up being, we're going to cross out the 0.5s. And so we're always going to have still arctan of y prime over x prime. And so we're still going to get the same angular result regardless of what the scaling is for the magnitude of the joystick values. Are there any questions about that? I kind of went through that kind of fast. Okay. Let's see where we're at. Yeah. So we've got enough time, I think, to cover the driver profiles real quick. I won't go into like a lot of detail because if we want to go into full detail, we would also talk about dashboard code. And I've got on here a separate set of potential sessions dashboard code. So I'll just talk about it in sort of broader terms. So all of these scaling factors, the exponent and the deadband, have very significant impacts on how the joystick feels to the driver, how their actions make the robot behave. And so it is preferable to be able to tune the exponent and the deadband to each individual driver. And because sometimes we don't know ahead of time which driver is going to be driving, or we want to be able to change quickly if we need to, we have the ability to have a different driver profile. So we can select different drivers who are driving, and that will change the values that are being used for either the deadband or the scaling values. And the way that works is that if you look at the front panel here, we've got the deadband and the deadbands for the strafe joystick, which is that magnitude of the X and the Y together. And then also the deadband for the rotation joystick, the scaling for, this is the exponent, so the scaling for the strafe and the scaling for the rotation. And all of these controls, these sliders, are actually inside of an array. And so if we click up on this button, we can actually see that different array elements have different values. So each driver gets one array element. So each driver gets a set of these 4 values. So like driver 0 has these 4 values, and then driver 1 would be these 4 values. And you can see how I think that the strafe scaling is different for driver 1 compared to driver 0. And on the code side of this, what we've got are these arrays containing the values for each individual driver. And then I'll talk about this in a second, but the value that's stored in the blue line is the driver number. So this is based off of the drop-down menu on the dashboard, saying whether you selected driver 0 or 1 or 2 or 3. It's pulling the correct index from the array, and the deadband and scaling values appropriate for that driver are then used throughout the rest of the code. So those are the ones that get put into the joystick scaling and are used in some of this earlier code, which we'll talk about later. Because it's kind of hard to remember who's driver 0 and who's driver 3, the drivers are named on the drop-down menu with their actual names. And so we've got a global variable called legal drivers that stores a list of all the drivers that we set up profiles for. So you know where to change that. If we go to the initialization folder and then go to initialize constants, we can see our list of legal drivers. So right now we've got Adam, Amelia, Ethan, Amelie, and autonomous. So autonomous in our structure does actually need its own driver profile. And if we have time, we can talk some about that. So those are our list of legal drivers. This list of legal drivers also appears on the dashboard. And the information that we're getting back from the dashboard is the driver number that's selected. This will display the current driver's name, so it's a little bit clearer whose drive profile you're editing at any given time. And then that number goes to the array indices. The other thing that's happening here is when you change the driver profile on the dashboard, and this actually happened once while we were tuning Ethan's driver profile this year. We put Ethan in his driver profile, but then continued editing, I think, Adam or Amelia's driver profile. And so none of the changes that we were making were being felt by Ethan. So the way to get around this is if you hit this sync driver profile button, what will happen is that it will look at the driver profile that's currently selected on the driver station and automatically change the values in the array indicators to the correct element, so that you'll be changing, so you'll be changing the values for the current driver. Now, you might ask why this is a button as opposed to it just always making sure that these indicators are changed or are matching the value in the dashboard. The problem is that when the robot code is running live, so we're deployed and we're changing the values on the laptop, that's okay. But when we're out there on the field and the code is only running on the robot and not running on the laptop, there are no indicators. And it turns out that LabVIEW actually crashes when you try to change an indicator that doesn't actually exist on a real user interface. And so we do have to have this button so that we can turn it on when we want to, but we do have to make sure that it's turned off when the robot is actually running by itself. And I'm not going to go into how to use these blocks right now. If people choose to do the dashboard code sessions, we'll talk about them. But essentially, these blocks allow you to change values, to actually change the indicator. So you could, in your code, change the color of the slider or change the font size of the values in here based on the code. So everything that you can sort of manipulate as a user on the front panel, you could also change in code using these nodes. And again, we talk more about that in the dashboard code. And Alex would like to remind everyone that during this entire process, Ethan did experience a placebo effect where he thought that we were actually changing the values even though we weren't. and was telling us that he liked one set of values over the other set, even though they were actually identical. So if anyone wants any evidence of how the placebo effect works, just go talk to Ethan. Are there any questions about the driver profiles and at least what they are and why we have them? Okay, so that is all I think we're going to talk about today.